Welcome to the deep dive. Today we are taking a torch to, well, probably the single most dense, but arguably the most important topic for anyone working in evidence-based medicine: biostatistics and research principles.
It really is. It's kind of the operating system of clinical practice, isn't it? If you are a GP trainee preparing for high-stakes examinations like the AKT, or, you just want to read a medical journal article without your eyes glazing over by the second paragraph, this deep dive is definitely for you.
Exactly. Our mission today is to cut through the jargon, really transform those dry definitions and, frankly, bewildering equations into practical, high-yield knowledge. We're going beyond just the what and diving straight into the why, understanding how these principles dictate whether or not you should change your practice tomorrow.
And the sources we're drawing on, they're structured. They come from a comprehensive set of foundational handbooks on these topics. So we're aiming to provide a structured overview of the entire field, ensuring that when you encounter a p-value or maybe a confidence interval or a test selection question, you approach it with, well, clarity and confidence.
Yeah, we're not just creating flashcards here. We are building a robust framework for critically appraising the literature. You really need to master the language of evidence, ensuring that no concept is overlooked, and that you understand the immediate clinical relevance of statistical findings.
We have to move past seeing these concepts as merely hurdles for an exam. They're essential tools for evaluating the trustworthiness of any guideline or research paper. I mean, this is the difference between just consuming information and truly evaluating it.
Okay, let's start at the absolute ground floor. The data itself. I mean, the most fundamental decision in statistics is determining what kind of number you actually have, because the test you run depends entirely on it. We basically categorize everything into two main groups: quantitative and qualitative data.
Right. Quantitative data first. Deals with quantities, obviously. Measurable numbers. And this is where we immediately split into continuous and discrete types.
Continuous data, that's the high-precision stuff, isn't it? It can theoretically take any value within a range. Think decimals, fractions, maybe highly precise instrument readings. And the sources give us a critical split here: interval versus ratio. This is a distinction that frequently trips people up.
It really does. So interval data has equal distance between values, which is key. For example, the difference between 10 degrees Celsius and 20 degrees Celsius is exactly the same as the difference between 30 and 40. But here's the catch. It can be negative, and the 0 point is arbitrary. It's not a meaningful zero. Temperature is the classic example because 0 degrees Celsius doesn't mean the absence of heat, right?
Which brings us nicely to ratio data. Okay, so it shares that equal distance property with interval data, but ratio data possesses a true 0 point. Zero actually means the complete absence of the measured quality.
Exactly. Things like weight, height, drug concentration, or, say, the absolute number of bacterial colonies, none of these can be negative. If you have 0 weight, you have, well, the absence of weight. That true 0 point allows us to form meaningful ratios, like saying 20 kilograms is twice as heavy as 10 kilograms. You just can't do that with Celsius temperatures.
Okay, makes sense. Then we shift to discrete quantitative data. This is still numerical, but it can only take a limited countable number of values. They're usually whole numbers.
Yeah, like the number of GP appointments booked in a day or the count of relapses a patient has had in a year. You can't have 3.7 relapses, can you?
Yeah.
It's count data, often fixed. Integer values.
Right. So moving over to qualitative data now, this is the descriptive, non-numerical, or categorized information. We can start with nominal data. Nominal, meaning named, basically classifies things without any implied order.
Like blood type A, B, O, or ethnic group, or favorite color. These are just categories, and one isn't statistically better or worse than the other. This is crucial because if you try to take the mean of blood types, the number you get is completely meaningless.
But if we introduce an order or perhaps a rank, we move to ordinal data. Think of those patient satisfaction surveys: poor, fair, good, excellent, or maybe cancer staging, stage 1, 2, 3. We know stage 4 is worse than stage 1. There's a clear order.
But the caveat with ordinal data, which is absolutely vital for test fiction later, is that we don't know if the distance between poor and fair is the same numerical distance as the gap between good and excellent. Because we can't assume those equal intervals, we can't use parametric tests designed for means and variances. That's a key point.
Definitely. And finally, a really common scenario in clinical practice: binomial data. This is a specific type of qualitative data with only two possible outcomes.
Yes, no. Alive, dead, passed, failed, treated placebo. Just two options.
These distinctions aren't just academic exercises, are they? If you wrongly treat ordinal data like a pain scale, as if it were continuous data and run, say, a t-test, Your statistical assumptions are violated. Your results could be completely invalid.
Absolutely. This is step 0 for critical appraisal. Get the data type right first. #tag 1.2 central tendency and spread.
Okay, so once we have our data and we know what type it is, we need tools to summarize it. Let's work through the foundational descriptive statistics using that sequence provided in the source material. 32339785.
Right. We summarize data using measures of central tendency where the middle is, and measures of spread how dispersed it is. The most common measure of central tendency is the mean, the average. We just sum all the values and divide by the count, which is 9 in this case.
Okay, so the sum is 45. Divided by 9, the mean is exactly 5. Easy enough to calculate, but as you hinted earlier, often the least robust measure.
Yeah, why is it less robust? Because the mean is so easily pulled by outliers. If that 9 in the sequence were a 90 instead, the mean would shoot up dramatically, wouldn't it? It wouldn't really represent the center of the majority of the data points anymore.
That's where the mode comes in handy sometimes. It's simply the value that appears most often. In our sequence, the number 3 appears 3 times, more than any other, making it the mode. It's useful for categorical data, but, often less informative for continuous numerical data.
And then we come to the median, the middle value. Now, to find it, you must first order the sequence. 2, 3, 3, 3, 5, 5, 7, 8, 9. Since we have 9 points, an odd number, the middle one, the 5th number, is 5. So the median is 5.
And the median superpower, particularly in clinical research, is that it is resistant to those extreme outliers we talked about. If we change that 9 to 90, the median would still be 5. That hasn't changed at all.
Exactly. Which is why for things like income data or skewed clinical data like length of hospital stay maybe, the median is often preferred over the mean. It gives a better sense of the typical value.
And we absolutely must solidify the rule for when there's an even number of integers. What if we had 10 numbers in our sequence?
Good point. If you had 10 numbers, once they're ordered, the middle 2 are the 5th and 6th values. You simply average those two to find the median. So, for example, if the middle 2 ordered values were 4 and 5, the median would be 4.5. You take the exact midpoint. It's a necessary detail.
Right. Calculate the midpoint. Got it. Finally, the simplest measure of spread, the range. Just the maximum value minus the minimum value. Here at 9 minus 2 equals 7. It gives us a quick snapshot of the data's overall dispersion, how wide it stretches.
A quick snapshot, yes. But like the mean, it's entirely dependent on just those two extreme values. #tag 1.3, the shape of data, parametric requirements.
Okay, let's talk about the shape, the geometry of the data distribution. Why is the shape so important? Well, because it acts as a gatekeeper, doesn't it? It decides which powerful statistical tests, the parametric tests, we are actually allowed to use.
Exactly. Parametric tests rely on some pretty strong assumptions about the population distribution. If your data is robust and symmetrical, it generally follows the normal distribution, that famous Bell's curve. And if data is normally distributed, the mean, the median, and the mode are all equal, all lined up at the peak. This symmetry is basically the green light for high-powered tests like the t-test and ANOVA.
But medical data, especially things like disease severity scores or maybe length of stay, often doesn't cooperate. It's often lopsided. When the data is lopsided, it is non-parametric, and we describe it using skew.
Let's start with positive skew. Imagine the bulk of your data points are clustered on the left, but there's a long tail stretching out to the right, towards the more positive values. Think of reaction times, maybe. Most are quick, a few are very slow.
Right, and that long positive tail is pulling the average higher. So the mean gets pulled the furthest in the positive direction. The relationship becomes mean-median mode. A quick way to visualize this clinically is maybe waiting times in A&E. Most people wait a relatively short time. That's the bulk of data on the left. But a few wait a very, very long time. That's a long positive tail. And that drags the average waiting time up.
Conversely, you have negative skew. Here, the tail stretches out to the left, towards the negative or lower values.
So here, the mean is dragged down by those few very low values.
Yeah.
The relationship reverses. The mode is the peak still, so it's the largest value, followed by the median, and the mean is pulled down, making it the smallest. So mean-median mode.
And this skew relationship is often tested, because it forces you to immediately recognize that the mean is no longer the appropriate measure of central tendency in skewed data. You should really default to the median to describe the typical value.
So if your data is heavily skewed, you really have to abandon those parametric tests. They're just unreliable when the normality assumption is violated, and you need to move to the less powerful, perhaps, but more appropriate non-parametric equivalents.
Which we'll get to very shortly in the test selection part. Understanding the shape dictates the path forward.
Okay, we've established how to describe data. Now let's move into the process of scientific inference, using a small sample, our study group, to draw a conclusion about a much vast population. This entire process really revolves around the null hypothesis. Hashtag tag tag 2.1, the logic of the null hypothesis.
The null hypothesis, often written as HA, is kind of the necessary friction in the research engine. It's the default assumption. It states that the effect you are looking for, the difference you think you observed, is simply due to chance or random sampling error. It basically posits that there is no difference.
Let's use that clinical example again. Say we want to prove that drug A is better than drug B at lowering a patient's blood pressure over 6 months. What must the researchers assume initially before they even start analyzing?
They must assume the null hypothesis is true. They have to assume that there is no difference in the effectiveness of drug A and drug B in lowering blood pressure. The results are assumed to be equal, and any perceived difference is just random noise. The entire study is then designed to gather enough convincing statistical evidence to destroy or reject that initial assumption. We are essentially testing the plausibility of that no difference scenario. Hashtag tag 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 2.2 statistical errors in power.
Okay, so when researchers make that crucial decision to reject the null hypothesis or fail to reject it, they face two fundamental risks of being wrong. These are the type I and type 2 errors.
Right. Type I error, represented by the Greek letter alpha, Ava, is essentially a false positive. This is claiming an effect or a difference when, in reality, none exists. You reject the null hypothesis and declare drug A is better when, in fact, they were equal all along.
And clinically, this is dangerous, right? Because it could lead to new, potentially expensive, or even harmful treatments being adopted based on what was just a random fluke in the data. That alpha level is usually set beforehand, typically at 0.05, which links directly to the p-value threshold.
Exactly. Then there's the type 2 error, represented by beta. This is the false negative. This means you failed to detect a real effect that was actually there. The drug really was better, but your study results weren't strong enough, maybe the study was too small, and you ended up failing to reject the null hypothesis. You conclude there's no difference when one truly exists.
And the clinical danger of a type 2 error is perhaps less immediately obvious, but still significant. An effective, beneficial, maybe even life-saving treatment might be incorrectly shelved or dismissed because the study simply lacked the ability to find the difference. It lacked power.
Precisely. That ability, the probability of correctly rejecting the null hypothesis when it is false and a real effect exists, is called statistical power.
So power is essentially the probability of finding a real difference if it's there.
Correct. Power is calculated as $1 beta, 1 minus the probability of a type 2 error. It's the probability that your study will detect a difference if one is truly there to be detected. And what's fascinating here is the direct sort of structural link between power and study size.
So the larger the sample size, the n, the smaller the inherent random variability or noise in the data, and thus the higher the power.
Exactly that. A small study inherently has low power and therefore a high risk of committing a type 2 error, missing a clinically important effect just because it didn't have enough participants to reliably detect it.
That makes sense. That's why researchers calculate the minimum sample size needed before starting a trial, isn't it? They often aim for something like 80% power.
Yes, 80% power, which means accepting a beta, a 20% risk of a type 2 error, is a very common target. It's generally seen as an acceptable trade-off against the risks of a type IR, alpha, usually 5%. You're balancing the risk of wrongly claiming an effect versus the risk of missing a real one. Hashtag tag 2.3 p-value interpretation.
Okay, let's talk about the p-value. It's the mathematical output that usually governs the rejection of the null hypothesis, but it's probably the most misused and misunderstood number in all of medicine. What is its precise definition?
Okay, precisely. The p-value is the probability of observing a result as extreme as or even more extreme than the one you actually observed in your study, assuming the null hypothesis is true. Essentially, it's the probability that your findings could have occurred purely due to random chance if there was really no underlying effect.
So let's say we compare drug A and drug B and we get a p-value of 0.8. That means there's an 80% chance that the difference we saw, or an even bigger one, could happen just by chance, even if the drugs were actually identical in effect.
Exactly. An 80% chance the null hypothesis could produce such a result. Clearly, that's not statistically significant. We wouldn't reject the null hypothesis there.
But if the p-value is low, say p-val 0.02.
Well, if p-value is low, the probability of the finding being just random chance is low, and we gain confidence in rejecting the null hypothesis. The traditional threshold, as we said, is p.05. This means there is less than a 5% chance, or less than 1 in 20, that the observed results occurred randomly if the null was true. Once we cross that threshold, we conventionally deem the findings statistically significant.
It's really paramount, though, isn't it, to remember what the p-value is not. It's not the probability that the research hypothesis is correct, and it's definitely not a measure of the size or clinical importance of the effect.
Absolutely critical distinction. A p0.001 just means the difference observed is very, very unlikely to be due to chance. It doesn't automatically mean the drug is twice as good or that the effect is clinically meaningful. It just signals that something other than chance is likely going on. Hashtag tag 2.4 paired versus unpaired data.
Right. Before we jump into that crucial test selection matrix, we need to solidify one more concept: the difference between paired and unpaired data. This is often the next logical branching point in deciding which test to use.
Yes, very important. Paired data means the two sets of measurements are inherently dependent or linked, usually because they come from the same individuals, or maybe from carefully matched pairs, like twins or matched controls. The key is that the same subject often serves as their own control.
Clinically, you might think of measuring, say, cholesterol levels in a group of patients before and after 6 months on a new statin. The pre-treatment level is naturally related to the post-treatment level within each individual.
Exactly. That's sometimes called repeated measures data as well.
Okay. And unpaired data.
Unpaired data means the two groups being compared are independent and unrelated. The measurements in one group don't influence the measurements in the other group. A classic example is the randomized controlled trial, where one group receives the active drug and a completely separate group receives a placebo. The two samples are distinct sets of people.
And if you mix these up, if you use a paired test on unpaired data, or vice versa,
You choose the wrong test, fundamentally. The statistical calculation of error, standard error, becomes invalid because the tests make different assumptions about the relationship between the data points. We simply have to treat dependent data differently than independent data when we run the stats. Hashtag 2.5, navigating the test selection matrix. The three tables.
Okay, this is arguably the highest yield section for AKT prep and for reading papers critically. We need to decide which test to use based on the answers to a few key questions. 1, what's the data type? Is it numerical and normally distributed, parametric, or numerical but skewed, non-parametric, or is it categorical? 2, how many groups are we comparing? 1, 2, or more than 2? And 3, is the data paired or unpaired?
Exactly. Let's break it down table by table, starting with the ideal scenario, the one that allows the most powerful tests. Parametric tests. We're assuming here we're dealing with numerical data, interval or ratio, that is normally distributed, and we're usually comparing means. Hashtag parametric test. Numerical data, normal distribution. Okay, scenario 1. You are assessing the mean of just one group against some known standard or benchmark value. For example, comparing the mean blood pressure of your diabetic clinic patients against a national target. Here, you use a one-sample t-test.
Simple enough. What about comparing two groups? This is very common.
If the data is paired, remember, same patients before and after, or matched pairs, we use the paired t-test. This looks at the mean difference within pairs. If the data is unpaired to independent groups, like drug versus placebo, we use the unpaired t-test, which is sometimes called the independent samples t-test. It compares the means between the two separate groups.
Okay, one group, one sample T, two groups, paired T or unpaired T, depending on the setup. But what if we have 3 or more groups? Say we're comparing drug A, drug B, and a placebo group all at once.
All right, here's a critical concept. If you have 3 or more groups, you must use ANOVA, analysis of variance. You cannot just run multiple t-tests comparing A vs B, then B vs C, and then A vs C.
Why not? I mean, it seems logical to just compare them pairwise with t-tests. Why the jump to this different test, ANOVA?
It's about controlling the error rate. Running multiple t-tests inflates your risk of getting a type I error that false positive. If you set your alpha threshold at 0.05 for each t-test, and you run 3 tests, your overall chance of finding a fluke significant result somewhere across those tests becomes much higher than the 5% you intended. ANOVA performs one single omnibus test that looks for any significant difference among all the group means, while keeping that overall type I error rate at the desired level, usually 0.05.
Ah, okay. So ANOVA protects against inflating the false positive rate when comparing multiple groups. Makes sense. And what about relationships? If we're not comparing group means, but looking for an association between 2 numerical variables, both normally distributed, like height and weight.
Then we calculate a correlation coefficient using Pearson's product moment correlation, often just called Pearson's R. It measures the strength and direction of the linear relationship between those two continuous, normally distributed variables. Hashtag nonparametric tests, numerical data, skewed distribution.
Okay, but what if our numerical data isn't normally distributed? What if it's skewed, or maybe it's ordinal data like those rank scales? Or perhaps the sample size is just too small to confidently assume normality? Then we have to switch gears to non-parametric equivalence, right?
Exactly. We move to the nonparametric world. The core difference here, conceptually, is that these tests often don't compare means directly. Instead, they frequently work by comparing the ranks of the data values.
So they sort of ignore the actual numerical values and just look at their relative positions.
In essence, yes. They take the raw, potentially messy or skewed numbers, convert them into ranks, first, second, third, etc., and then perform statistical tests on those ranks. Now, this generally reduces their statistical power or sensitivity compared to their parametric counterparts. They're less likely to detect a true difference if one exists, but the huge advantage is that it makes them robust. They work even when the assumptions of normality are violated.
Okay, so what are the key non-parametric tests we need to know? Let's start with the paired data scenario. Again, like before and after measurements on the same person, but the data is skewed. What's the alternative to the paired t-test?
For paired data, or actually also when comparing the distribution of one group against a known median value, we use the Wilcoxon-signed rank test. This is the direct, non-parametric alternative to the paired t-test.
Wilcoxon signed rank. Got it. And for two unpaired independent groups where the data is skewed, what replaces the unpaired t-test?
The most common test there is the Mann-Whitney U-test. Sometimes it's called the Wilcoxon-Ransom test, which can be confusing, but Mann-Whitney U is the name you'll probably see most often. This is the non-parametric workhorse for comparing two independent groups when parametric assumptions aren't met. You'll see this test frequently cited in studies dealing with things like patient-reported outcome measures, PROMs, or satisfaction scores, which are often ordinal or skewed.
Mann-Whitney U for two unpaired groups. Okay, what if we have more than two independent groups, but the data is non-normal? What's the non-parametric equivalent of ANOVA?
That requires the Kruskal-Wallis test. This is the non-parametric equivalent to the one-way ANOVA for comparing three or more independent groups.
Kruskal-Wallis. Okay. And is there an equivalent for repeated measures, like if we measure the same skewed outcome on the same group at three or more different time points?
Yes, there is. If the data involves repeated measures across more than two time points or conditions on the same subjects, and it's non-parametric, you move to the Friedman test. This is the non-parametric alternative to repeated measures ANOVA.
Friedman test for repeated measures.
Right.
Right. And finally, correlation. What if we want to see if two variables are related, but one or both are ordinal, or the numerical data is skewed? What replaces Pearson's correlation?
That would be Spearman's rank correlation, often denoted by the Greek letter rho, or sometimes Turl-Anders. Similar to Pearson's, it measures the strength and direction of association. But like the other non-parametric tests, it does so based on the ranks of the data, not the raw values. So it assesses monotonic relationships. As one variable increases, the other tends to increase or decrease, rather than strictly linear ones. Hashtag categorical data, non-parametric.
Okay, that covers numerical data, both normal and skewed. Our third and final matrix deals exclusively with categorical data, things measured in counts, frequencies, or proportions, like presence or absence of a disease or number of patients in different treatment groups. These are inherently non-parametric, aren't they?
Yes, they deal with counts or categories, not measurements on a continuous scale. The cornerstone test here, the one you absolutely have to know, is the chi-squared test, often written as chi-stu-2.
Chi-squared. When do we use that?
Its most common use is for comparing proportions or frequencies between two or more unpaired or independent groups. For example, if you are comparing the proportion of patients who develop a side effect, say a rash, in a group taking drug X versus a group taking a placebo, you'd set up a 2x2 table, group versus rash no rash, and run a chi-squared test to see if the proportion getting the rash is significantly different between the groups.
Okay, so comparing proportions in two independent groups. We often see it used with those 2x2 tables. But are there limitations? Does it always work?
There's a key assumption regarding sample size, or more accurately, the expected cell counts within that contingency table. If the expected count in any of the boxes or cells of the table drops below a certain threshold, commonly cited as 5, the chi-squared approximation becomes inaccurate.
And if those expected counts are too small, what's the alternative for comparing two unpaired groups with categorical data?
In that situation, particularly for 2x2 tables with small expected frequencies, You must use Fisher's exact test. It calculates the exact probability without relying on the approximation used by chi-squared, so it's accurate even with very small numbers.
Fisher's exact for small counts in 2 by 2 tables. Okay. But the chi-square test seems quite versatile. Does it handle more complex situations?
Yes, it's quite flexible. It's also the standard test used for any scenario involving categorical data with more than 2 categories in the outcome. In GG, comparing improvement rated as poor, fair, good across groups, or when comparing proportions across more than 2 independent groups. UG, comparing side effect rates across drug A, drug B, and placebo. Essentially, if you're comparing frequencies or proportions in an independent manner involving tables larger than 2 by 2, chi-squared is usually the go-to test, provided those expected cell counts are large enough.
Right, so chi-squared is the main player for independent categorical data. Now, the tricky one, what about paired categorical data? Imagine we ask patients a yes-no question, like, do you feel breathless walking uphill, before an intervention, and then ask the same question again afterwards. The outcome is categorical, yes-no, and the data is paired because it's the same patients. We can't use chi-squared, right?
Correct. Chi-squared assumes independence. For paired nominal data like that, specifically a 2 by 2 table comparing paired responses, for example, tracking who changed from yes to no, no to yes, etc., you need the McNamara test. It's specifically designed to analyze changes in proportions within the same subjects over time or under different conditions. It focuses on the discordant pairs, the people who change their answer.
McNamara for paired categorical data. Okay, that matrix seems to cover most common scenarios. Knowing the data type, number of groups, and paired status really narrows down the choice. So that matrix gives us the tools to decide if an observed effect is likely real or just chance. But once we think we have a real effect, we need to know how precise our measurements are, how much uncertainty is there around our findings. This brings us back to measures of spread, starting with the standard deviation, tag 3.1 standard deviation, and the normal curve.
Right. Standard deviation, often abbreviated as SD, or represented by the Greek letter sigma,
Yeah.
is the most commonly used measure of spread or dispersion in normally distributed data. It basically tells us, on average, how far individual data points tend to fall from the mean of the sample. And crucially, as we said, its interpretation relies heavily on the data following that normal distribution, the bell curve.
You defined it earlier mathematically as the square root of variance. We should probably pause there for a second. What exactly is variance? It sounds related but different.
It is. Variance is essentially the average of the squared differences of each data point from the mean. Think about it. If you just calculate the difference of each point from the mean, some will be positive, above the mean, and some negative, below the mean. If you simply average those raw differences, they tend to cancel each other out, maybe even summing to zero. That's not helpful for measuring spread.
So to get around the positive and negative values canceling out, we square every difference first. That makes them all positive.
Exactly. We square each deviation from the mean, then we average those squared deviations. That average squared deviation is the variance.
But squaring changes the units, doesn't it? If we measured height in centimeters, the variance would be in square centimeters, which is weird to interpret.
Precisely.
Yeah.
So because squaring changes the unit of measure, we take the square root of the variance to return the measure of spread back to the original units of the data. And that square root of the variance is the standard deviation. It's back in centimeters, or whatever the original unit was.
Okay, that makes sense. Variance is the average squared distance. SD is the square root to get back to original units. And the SD is the key to interpreting that normal curve.
It is. The mean mid in population terms, or M or tobar in sample terms, sits right at the center peak of the bell curve. The standard deviation represents the distance from that mean to the curve's inflection point. That's the point where the curve switches from bulging outwards, convex, to curving inwards, concave.
And that leads us to the empirical rule, sometimes called the 68, 95, 99.7 rule, which is really essential for the AKT and just for general clinical interpretation of normally distributed data, right?
Absolutely fundamental. It tells us that for normal distribution, approximately 68% of all data points will fall within plus or minus 1 standard deviation of the mean. If you expand that out to plus or minus 2 standard deviations, you capture about 95% of the data. And going out to plus or minus 3 standard deviations encompasses virtually all the data, about 99.7%.
Knowing this rule allows you to immediately gauge where any given observation sits within the expected distribution. If someone's result is more than 2 SDs above the mean, you know they're in the top 2.5% or so.
Exactly. And we can standardize these positions using something called z-scores.
Z-scores, how do they work?
A z-score simply tells you how many standard deviations a particular data point or observation is away from the mean. It's calculated as observation mean standard deviation. So the z-score of +2 means that specific data point sits exactly 2 standard deviations above the mean. A z-score of -1 means it's 1 standard deviation below the mean.
And the advantage of z-scores is that they allow for standardization, right? You can compare things measured on totally different scales.
Precisely. It allows you to compare, say, the relative extremeness of one patient's height z-score to the relative extremeness of another patient's weight z-score, even though height and weight are measured in different units. It puts everything onto a common scale based on standard deviations from the mean.
And thinking back to the 68, 95, 99.7 rule, those really extreme values, the ones sitting beyond PM3 sigma from the mean, they make up that tiny remaining 0.3% of the data, split between the two tails. Those are the potential outliers, the really unusual observations.
That's right. Very unlikely to occur just by chance if the data truly follows that normal distribution. Hashtag tag 3.2, standard error of the mean, SEM.
Okay, so standard deviation describes the spread or variability within our single sample of data. But clinical research isn't usually just interested in the sample itself. We want to infer something about the wider population from which the sample was drawn. This is where the standard error of the mean, or SHEM, comes in. It sounds similar to SD, but it's different, right?
Very different, and a crucial distinction. The standard error of the mean, SEM, is not about the spread of individual data points within your sample. Instead, it measures the precision of your sample mean as an estimate of the true unknown population mean.
So it's about how much variability we would expect to see in the sample means themselves if we were to draw multiple different random samples from the same underlying population.
Exactly that. It tells us how precisely our calculated sample mean, let's call it auto dollar, estimates the true underlying population mean, often denoted by JAMA. A smaller SEM means our sample mean is likely closer to the true population mean. A larger SEM means there's more uncertainty.
And how is it calculated? Is it related to the standard deviation?
Yes, it's directly related to the sample standard deviation, SD, and critically, the sample size n. The formula really shows the key relationship, SD squared in a way.
Ah, okay. SCM equals the standard deviation divided by the square root of the sample size. That formula immediately tells us something important about the relationship between sample size and the precision of our estimate, doesn't it?
Absolutely. It shows an inverse relationship. The larger the sample size, the larger the denominator becomes, and therefore the smaller the SEM gets.
So bigger studies lead to smaller standard errors?
Precisely. A small SEM indicates that our sample mean is a better, more precise, more reliable reflection of the true population mean. This is absolutely crucial for assessing the reliability and trustworthiness of any study's findings. Larger samples give more precise estimates of the population mean. Hashtag 3.3 confidence interval, CI.
And the ultimate, most clinically useful application of the SEM is in calculating the confidence interval, or CI. This is a term we see reported in almost every medical paper. What exactly is a confidence interval telling us?
The confidence interval, CI, provides a range of plausible values for the true unknown population parameter, like the population mean, or a difference between means, or an odds ratio based on our sample data. Instead of just giving a single point estimate, like our sample mean, it gives a range within which we are confident the true population value likely lies.
So if a study reports, say, a 95% confidence interval for the mean weight loss with a new drug is 2 kilograms to 4 kilograms, what does that 95% actually mean?
Okay, the strict interpretation of a 95% CI is a bit frequentist. It means that if we were to repeat this exact study many, many times, drawing different samples from the same population, and we calculated a 95% CI from each study, then 95% of those calculated intervals would successfully capture or contain the true but unknown population mean weight loss.
Right. It's a statement about the reliability of the method used to generate the interval, not strictly the probability that this specific interval contains the true value, although we often interpret it that way in practice.
Exactly. And just like the SEM, the width of the confidence interval is directly related to sample size. A larger study sample size leads to a smaller SEM, which in turn leads to a narrower, tighter CI.
And a tighter CI is better, right? It signifies greater precision in our estimate. A very wide CI suggests a lot of uncertainty about where the true population value might be.
Absolutely. For a CI to be clinically useful, it ideally needs to be tight enough to help us make decisions. A CI for a treatment effect that ranges from a tiny benefit to a large benefit might not be as helpful as one that confidently points to a substantial benefit.
And how do we calculate the CI from the CM? You mentioned it uses the SCM.
It does. The most common CI is the 95% CI. To calculate this for a mean, we use the sample mean, the SEM, and a specific value from the standard normal distribution, the Z distribution. that corresponds to capturing the central 95% of the area under the curve. That value is approximately 1.96.
Ah, 1.96. That number pops up a lot. So the formula is something like CCI equals mean PM, 1.96 times SEM.
Exactly. You take your sample mean, calculate the SAM, multiply the SAM by 1.96. This product is often called a margin of error. And then you add and subtract that margin of error from the sample mean to get the upper and lower limits of the 95% confidence interval.
Okay, let's work through that numerical example provided in the sources. Say we have a study looking at the height of adult males. The sample size is $100. The calculated sample mean height is 175 textall, and the standard deviation within the sample is $5 textkuntiger. Let's calculate the 95% CAR for the true population mean height.
Okay, step 1. Calculate the SEM. We use the formula CMSD.
Okay.
So the CM all's 5
The square root of 100 is 10, so something M equals 5 $10, which equals 0.5 centimeter.
Correct. Step 2, calculate the margin of error by multiplying the CM by 1.96. So margin of error, 1.96 times 0.55.
1.96 times 0.5 is 0.98 centimeters.
Right. Step 3, calculate the lower and upper limits of the 95% CI using mean PM margin of error. The lower limit is $175.98.
Which is $174.98.
So based on our sample, we are 95% confident that the true average height of the population from which this sample was drawn lies somewhere between 174.02 centimeters and 175.98 centimeters.
Exactly. And notice how the sample size of 100 helped make that interval relatively narrow. Now, the critical point for interpreting confidence intervals clinically, especially when comparing groups or looking at treatment effects, is checking if the interval crosses the null value, isn't it?
Absolutely essential. For a mean difference between two groups, a difference in blood pressure reduction between drug and placebo, the null value, representing no difference, is 0. For ratios, like risk ratios or odds ratios, or R, the null value representing no difference in risk or odds is 1.
So if the 95% CI for a mean difference includes 0, for example, if the CI runs from -2 mmHg to +5 mmHg, what does that tell us?
It tells us that we cannot confidently exclude the possibility of there being no difference, 0, between the groups. Even if the point estimate, the sample mean difference, was, say, plus 1.5 mmHg, the CI indicates that the true difference could plausibly be 0, or even slightly negative. Therefore, the result is not statistically significant at the 0.05 level.
So the CI gives us more information than just the p-value. It provides a range for the likely magnitude of the effect, and it tells us about statistical significance based on whether it crosses that null value.
Precisely. The confidence interval is arguably much more informative for clinical decision-making than a simple p-value alone. It gives you the precision of the estimate and the range of plausible true effects.
Okay, we've covered describing data and making inferences with statistics. Now let's shift gears and look at the frameworks, how we actually structure the investigation to collect those numbers reliably in the first place. Research methodology and study design. Tag 4.1, research types and data collection methods, qualitative versus quantitative.
Yes, and we need to remember that fundamental distinction we touched on earlier. Quantitative research versus qualitative research. Quantitative seeks to measure, count, generalize, and predict using objective numbers and statistical analysis.
While qualitative research seeks to understand, describe, explore experiences, beliefs, or social contexts using words, narratives, observations, it's more about depth and meaning than numerical measurement. Both are valid, of course, but they answer different kinds of research questions.
Exactly. So let's look at some specific data collection methods and study types mentioned in the sources. Often, before embarking on a large, expensive trial, researchers might conduct pilot studies, or sometimes called feasibility studies, or vanguard studies.
These are like test runs, aren't they? Small-scale versions.
Pretty much. They are small, relatively low-cost studies whose main goal isn't actually to find a definitive answer to the research question, but rather to test and perfect the methods. They help iron out logistics, check recruitment strategies, refine data collection tools, and generally ensure that the larger definitive trial is actually achievable, ethical, and likely to run smoothly.
Makes sense to do a dry run. Then we have foundational tools like questionnaires. Very common.
Very common. They're great for collecting standardized, objective data quickly from a large number of people. However, their utility is really bounded by how well they are designed. And you always have the risk of issues like poor participant recall. Can people accurately remember their diet from last week? Or social desirability bias. People giving answers they think you want to hear.
Right. What about field observations?
Field observations involve researchers directly watching behavior or events in the participant's natural environment. This can lead to very rich contextual data that you wouldn't get from a questionnaire. The limitation, though, is usually time. They can be very labor-intensive, and there's always the risk of documentation error or even the Hawthorne effect, where the very act of being observed changes the behavior the researcher is trying to study.
People behaving differently because they know they're being watched.
Oh.
Okay, then there are focus groups.
Focus groups are essentially structured group interviews. They're quite efficient for exploring shared belief systems, attitudes, or group consensus on a topic relatively quickly. They're excellent for qualitative data collection, often exploring the why behind people's opinions or behaviors, and they benefit from the dynamic interaction and discussion between participants.
So more interactive than individual interviews. How about ethnography? That sounds a bit more involved.
It is. Ethnography is a deeper, more immersive, qualitative study approach, often used in fields like anthropology, sociology, but also in public health or community medicine research. The researcher typically embeds themselves within a specific community or social setting for an extended period to gain a really profound insider insight into social interactions, culture, norms, and practices. It often uses a combination of methods like participant observation and in-depth interviews. It provides a level of context that simple statistics often miss entirely.
Right, really understanding the lived experience. Now, two methods mentioned that seem focused on reaching conclusions or building theory. The Delphi method and grounded theory. What's the Delphi method about?
The Delphi method is quite fascinating. It's a structured, iterative process specifically designed to reach consensus among a panel of experts on a particular topic where evidence might be scarce or opinions divided. Critically, the experts provide their opinions or forecasts anonymously, usually through questionnaires. Then, the results are collated, summarized, and fed back to the panel in subsequent rounds. They can then revise their opinions based on the group feedback.
And the anonymity is key.
Absolutely. It removes the potential influence of dominant personalities, seniority, or groupthink, allowing for a more genuine, structured consensus to emerge based on the collective, considered judgments of the experts.
Interesting. And grounded theory, that sounds like it starts from the ground up.
It does. Grounded theory is a systematic, inductive method used primarily in qualitative research. Instead of starting with a pre-existing hypothesis and designing a study to test it, which is a deductive approach, grounded theory aims to generate a new theory directly from the systematic analysis of the research data itself. You collect data, analyze it, identify patterns and concepts, and build a theoretical framework that is grounded in those observations. It's often used when studying novel social processes or phenomena where existing theories might not fit well.
So theory emerges from the data rather than the other way around. Okay. And finally, the case study.
Case studies involve an in-depth, detailed analysis of a single case or a small number of cases, like an individual patient, a clinic, or an event, often studied over a long duration. They provide rich, descriptive depth and often integrate both qualitative data, like patient interviews, and quantitative data, like clinical measurements. They're crucial for exploring complex situations, generating hypotheses for further research, or illustrating unique clinical presentations. However, their major limitation is that findings from one or a few cases are very weak for establishing generalizable cause and effect relationships. Hashtag 4.2 hierarchy of evidence. Ecoism.
Now, when a busy GP trainee is faced with multiple different sources of evidence on a clinical question, maybe meta-analysis, an RCT, an observational study, some guidelines, they need a way to quickly gauge which source generally commands the most respect, which is considered the most trustworthy. This is where the hierarchy of evidence comes in.
Exactly. It's a way of ranking study designs based on their potential to minimize bias and establish causality. We can use that helpful mnemonic ecoism, although the S is sometimes debated, running generally from the strongest evidence down to the weakest.
Okay, let's list them out. At the very top, we have meta-analysis. Then comes systematic review. Below that, interventional studies like randomized controlled trials, RCTs. Then observational studies, followed by case studies reports. And finally, at the bottom, expert opinion or basic science research.
Right, and it's really important to nail down the difference between the top two, meta-analysis and systematic review, as they're often confused but are not the same.
Okay, so what's a systematic review?
A systematic review is a rigorous qualitative summary of existing research on a specific clinical question. It involves a predefined, systematic approach to identify all relevant high-quality studies on the topic, critically appraise them for quality and bias, and then synthesize their findings descriptively. It essentially aggregates the current state of knowledge from multiple studies.
So it gathers and summarizes, but doesn't necessarily crunch the numbers together.
Correct. That's where the meta-analysis comes in. A meta-analysis is essentially a systematic review plus statistics. It takes the quantitative data, the numerical results, from multiple comparable high-quality studies identified in the systematic review, usually RCTs that are sufficiently similar or homogeneous, and then pools this data together using statistical methods.
Why pool the data? What's the advantage?
By pooling the data, you dramatically increase the overall effective sample size. This increased statistical power allows the meta-analysis to generate a single, more precise, weighted estimate of the treatment effect, like an overall odds ratio or mean difference, with a much narrower confidence interval than any individual study could provide. That increased precision and power is why meta-analyses sit at the very top of the evidence hierarchy, assuming they're done well.
Makes sense. More data, more power, more precision. And below these reviews.
Below meta-analyses and systematic reviews, we have the primary interventional studies, with RCTs being the gold standard because randomization helps control for confounding. Then come observational studies, which are inherently weaker because the lack of intervention in randomization means there's a higher risk of confounding and bias creeping in. And, as we noted, case studies and expert opinion are at the bottom, useful perhaps for generating ideas or understanding context, but definitely not for establishing reliable cause and effect. Hashtag 4.3 observational studies, the 3Cs. Okay, let's dig into those observational studies a bit more. These are studies where the researcher imposes no intervention. They simply observe what happens naturally in different groups of patients. The sources highlight three main types, often remembered as the 3Cs: cohort, case control, and cross-sectional. Exactly. Let's start with cohort studies. These are typically prospective studies. They follow groups forward in time. You generally select a group of individuals who are exposed to a particular factor, like, say, heavy salt eaters, and another group who are not exposed, the low salt eaters, ensuring both groups are initially free of the outcome you're interested in, like hypertension. You then follow both cohorts over time, often years, to see who develops the outcome.
So you start with the exposure and look for the outcome developing later. What's the strength of this design?
The main strength is that because you establish the exposure before the outcome develops, cohort studies allow you to establish the temporal sequence more clearly, which strengthens the argument for causality compared to other observational designs. They also allow you to calculate the true risk of developing the outcome in each group, and therefore the risk ratio, RR, comparing the exposed and unexposed groups.
But what are the downsides? Following people for years sounds challenging.
It is. The major challenges are the immense timescale often involved, especially for outcomes that take a long time to develop or are rare. This also makes them very expensive. And over that long time frame, there's a significant risk of attrition bias participants dropping out of the study. If the dropouts are different from those who remain, e.g. sicker people drop out more often, it can seriously bias the results.
Okay, so time, cost, and dropout are issues. How do case control studies differ?
Case control studies work the other way around. They are typically retrospective. They look backward in time. You start by identifying individuals who already have the outcome or disease of interest. These are the cases, e.g. people already diagnosed with hypertension. Then you select a comparable group of individuals who do not have the outcome. These are the controls. You then look back into the past history of both groups to compare their previous exposure to the factor you suspect might be linked. For example, you ask both groups about their past salt intake.
So you start with the outcome and look back for the exposure. What's the advantage here?
Case control studies are highly valuable, especially for studying rare diseases or outcomes with long latency periods. Because you start with people who already have the disease, you don't have to wait potentially decades for enough cases to occur, making them much faster and cheaper than cohort studies.
But what can you calculate from them? If you start with the outcome, you can't calculate the risk of developing it, can you?
Correct. Since you start with fixed numbers of cases and controls, you cannot calculate incidence or true risk. Instead, you calculate the odds of having been exposed in the case group compared to the odds of having been exposed in the control group. This gives you the odds ratio, or R, which estimates the relative risk but isn't quite the same.
And the main weakness of looking backward.
The biggest weakness is a significant potential for recall bias. Participants, especially cases who might be searching for reasons for their illness, may remember or report their past exposures differently or inaccurately compared to healthy controls. There's also a risk of selection bias in choosing appropriate controls.
Okay, so cohort is forward, exposure to outcome calculates RR, case control is backward, outcome to exposure calculates OR. What's the third C, the cross-sectional study?
A cross-sectional study is essentially a snapshot in time. You take a defined population, or representative sample of it, and you measure both the exposure status and the outcome status simultaneously at a single point in time. For instance, you might survey people in a town to determine the current prevalence of asthma and, at the same time, ask them about their current smoking habits.
Snapshot, measuring everything at once. What are these useful for?
They are relatively quick, easy, and inexpensive to conduct. They are excellent for determining the prevalence of a disease or condition in a population at a specific moment, how many people have it right now. They can also be useful for generating hypotheses about potential associations between exposures and outcomes.
But what's the major limitation of measuring everything at once?
The biggest limitation is that because exposure and outcome are measured simultaneously, it's usually impossible to establish the temporal sequence. You don't know for sure whether the exposure came before the outcome or vice versa. Did the smoking cause the asthma, or did people with respiratory problems perhaps take up smoking less often? This makes it very difficult to infer causality, leaving them highly vulnerable to bias and potentially reversing cause and effect. Hashtag tag 4.4 interventional studies and trial design.
Right, so observational studies, just watch. When we move to interventional studies, the researcher actually does something, performs a manipulation or action, like administering a new drug or implementing a specific therapy. The core goal here is rigorous control to try and isolate the effect of that specific intervention.
Exactly. And the gold standard within interventional studies is the randomized controlled trial, RCT. Its design relies on several key pillars to minimize bias and allow strong causal inference.
Let's break down those pillars. First, randomization. Why is randomly assigning patients to groups so important?
Randomization is the cornerstone. By using a random process, like flipping a coin or computer-generated sequences, to allocate participants to either the intervention group, for example, new drug, or the control group, for e.g. placebo or standard care, you aim to ensure that both known and critically unknown confounding factors are, on average, equally distributed between the groups at the start of the study.
So it makes the two groups statistically equivalent or as similar as possible before the intervention even begins, reducing selection bias and confounding.
Precisely. It's the best method we have for creating comparable groups, so that any difference observed in the outcome at the end of the trial is more likely attributable to the intervention itself, rather than pre-existing differences between the groups.
Okay, randomization is key. What's the next pillar? Blinding.
Blinding, or masking, is crucial for minimizing performance and detection bias. We ideally prefer trials to be at least single-blind, which usually means the patients are unaware of whether they are receiving the active intervention or the control, e.g. the placebo looks identical to the drug. This helps prevent participant expectation bias, the placebo effect, or maybe the nocebo effect if they think they got the placebo.
So single blind hides it from the patient. What's double blind?
The superior design, especially when outcomes are subjective, is double-blind. This means that both the patients and the researchers or clinical staff who administer the treatments and, importantly, assess the outcomes are unaware of who is assigned to which group.
Why blind the researchers too?
Blinding the researchers prevents them from consciously or unconsciously treating the groups differently or interpreting subjective outcomes like pain scores or rash severity in a biased way based on their knowledge of who got the active treatment. It minimizes observer bias and expectation bias on the part of the research team.
Okay, randomization and blinding. What's the third critical concept mentioned? Intention to treat, ITT analysis. This sounds important, but maybe counterintuitive.
It is absolutely critical for interpreting trial results in a real-world context. The intention to treat principle dictates that every patient who is randomized into the trial must be analyzed in the group they were originally allocated to, regardless of whether they actually received the intended treatment, completed the treatment course, dropped out of the study, or even switched over to the other group.
Wait, so even if a patient randomized to the new drug A group actually refused to take the medication after day 1 or they dropped out completely, we still include their outcome data, or lack thereof, in the analysis of the drug A group?
Yes, that's exactly what ITT means. Once randomized, always analyzed in that original group.
As a clinician, that sounds odd. If my patient in the drug A group didn't actually take drug A, doesn't counting them in drug A's outcome analysis just dilute the drug's true efficacy? It makes the drug look worse than it might be.
It absolutely can dilute the estimated treatment effect. It tends to make the difference between the groups look smaller than it might be if you only looked at perfect adherers. But, and this is the crucial point, that potential dilution is the price you pay to preserve the immense benefit of the initial randomization.
How does it preserve randomization?
Hmm. Because the reasons why patients don't adhere to treatment, drop out, or switch groups are often related to factors like side effects, worsening illness, perceived lack of efficacy that could bias the results if you selectively remove those patients from the analysis. If you only analyze patients who completed the treatment exactly as assigned, which is called a per-protocol analysis, you would destroy the randomization. The groups would no longer be comparable because you'd introduce selection bias, for example. The per-protocol group might consist only of the healthier, more motivated patients who tolerated the drug well.
Ah, I see. So the protocol analysis might show the drug's maximum potential effect in ideal circumstances, but the ITT analysis reflects what happens in the real world.
Exactly. The trade-off is this. ITT provides a more conservative, pragmatic, and generally more realistic estimate of the treatment's effectiveness when applied in a typical clinical setting, accounting for real-world issues like non-adherence and dropouts.
Oh.
It maintains the comparability achieved through randomization. Therefore, ITT analysis is considered the standard, preferred approach for analyzing RCT results, as it best reflects the likely impact of recommending that treatment strategy in practice.
Okay, so to trust that ITT result from an RCT, or indeed the findings from any study, we need some assurance that the study was well designed and conducted and as free as possible from systematic error. This brings us back to concepts like validity and bias. Hashtag 5.1, validity and reliability.
Yes, and we often hear the terms reliability and validity used, sometimes interchangeably, but they mean different things. Let's use that classic analogy of shooting arrows at a target.
Okay, the target analogy.
Reliability is about consistency or reproducibility. If you shoot several arrows at the target, do the shots cluster tightly together, regardless of where they hit? Can the measurement or the result be reproduced consistently each time the study is done or the measurement is taken? That's reliability. High precision.
And validity.
Validity is about accuracy. Did the arrows actually hit the bullseye? Is the study measuring what it is intended to measure? Is the result reflecting the true state of affairs? A measurement can be reliable, all shots clustered together, but invalid. The cluster is way off the bullseye. An unreliable measurement, shots scattered all over, cannot possibly be valid. So you need reliability for validity, but reliability alone doesn't guarantee validity.
Okay, reliable is consistent, valid is accurate, hitting the mark. And we can break validity down further, can't we, into internal and external validity.
Yes. Internal validity addresses the degree of confidence we have in the cause and effect relationship within the study itself. Did the intervention, the drug, truly cause the observed outcome, the improvement, or could the result be explained by other factors like confounding, bias, or chance? A study has high internal validity if it is well designed and executed, minimizing these potential alternative explanations. RCTs, when done well, generally have high internal validity due to randomization and blinding.
And external validity.
External validity, also known as generalizability, addresses whether the results of the study can be reasonably extrapolated or applied to people, settings, and situations outside the specific context of the study itself. For example, can the results from a highly specialized trial conducted in a tertiary academic medical center with very selective inclusion criteria be generalized to the much broader and more diverse patient population seen in typical general practice?
So a study could be internally valid, showing a real effect in its specific sample, but have low external validity if the sample or setting was very artificial or unrepresentative.
Precisely. There's often a trade-off. Highly controlled studies might maximize internal validity, but sometimes sacrifice external validity. Pragmatic trials often aim for a better balance.
And the sources mentioned triangulation. What's that in this context?
Triangulation is a technique often used, particularly in qualitative research, but also in mixed methods research, to increase the validity and credibility of the findings. It essentially means looking at the research question or phenomenon from multiple different perspectives or using multiple different methods. For example, you might use interviews, direct observations, and analysis of documents or records to study a particular issue. If the findings from these different approaches converge or support each other, it increases your confidence that the conclusions are robust and valid, giving you a more complete picture. Hashtag 5.2 bias and confounding systemic errors.
Right. So every study design choice, every decision made during conduct and analysis is essentially a fight against systematic error that can threaten validity. We already touched on confounding, but let's revisit it alongside bias.
Okay. Confounding, remember, occurs when some extraneous third variable is associated with both the exposure or intervention you're studying and the outcome you're measuring. and it distorts the apparent relationship between them. For instance, if you're studying the relationship between coffee drinking exposure and heart disease outcome, age is a potential confounder because older people are more likely to have heart disease, and they've likely been drinking coffee for longer. Age is linked to both, muddies the water.
And the best strategies against confounding are things like randomization in trials or in observational studies, trying to carefully match the comparison groups on known potential confounders, or using statistical adjustment techniques during analysis.
Exactly. Those are the main ways to try and control for confounding. Bias, however, is slightly different. Bias refers to a systematic error, not random error, but a flaw built into the study design, data collection process, or analysis that results in an incorrect estimate of the association or effect. Bias causes the results to consistently deviate from the truth in a particular direction, either overestimating or underestimating the true parameter.
And unlike random error, which might decrease with larger sample size, bias doesn't just go away if you collect more data using the same flawed method. It's built in.
Correct. Which is why identifying potential sources of bias is so critical when appraising a study. The list of potential biases is long, but the sources highlight several crucial ones that are essential recall for GP trainees, especially for the AKT.
Let's run through them.
Okay. Observer bias. This occurs when the researcher's knowledge of which group a participant is in, through anal treatment versus placebo, unconsciously influences how they measure or record the outcome, especially if the outcome is subjective. Double blinding is the primary defense here. Expectation bias. Similar, but can apply to the participant, placebo effect if they know they got the drug, or the researcher, interpreting results more favorably if they know it's the active treatment group. Again, blinding helps. Recall bias. We mentioned this with case control studies. Cases, people with the disease, may systematically recall or report past exposures differently, often more thoroughly or with perceived links, than healthy controls who have less reason to scrutinize their past. Big problem for retrospective designs. Publication bias. This is a bias affecting the literature as a whole. Studies with statistically significant positive results, showing a difference or an effect, are much more likely to be written up, submitted, accepted by journals, and published than studies with null or inconclusive findings, negative studies. This leads to an overestimation of treatment effects in the published literature because the failures often remain hidden in file drawers. Sampling bias, or selection bias generally, occurs when the sample included in the study is not representative of the target population to which you want to generalize the findings. For example, recruiting participants only via newspaper ads might miss certain demographic groups. Or, as mentioned before, recruiting only from a specialized tertiary care center might yield results not applicable to primary care. Anchoring bias. This is more of a cognitive bias in clinical decision-making, but can affect research interpretation. It's the tendency to rely too heavily on the first piece of information offered, the anchor, when making judgments. Workup bias, or verification bias. This is particularly relevant when evaluating diagnostic tests. It happens with the decision to perform the definitive gold standard test, for example, a biopsy to confirm cancer, is influenced by the result of the new test being evaluated. For example, if only patients who test positive on the new test routinely get the gold standard confirmation, while those who test negative often don't, it can falsely inflate the apparent accuracy, like sensitivity and PPV, of the new test because you miss confirming the false negatives. Lead time bias. This is a really tricky one related to screening programs. A screening test detects a disease earlier in its natural history than it would normally have presented with symptoms. This increases the measured time from diagnosis to death. However, if the screening doesn't actually change the time of death itself, i.e. doesn't ultimately prolong life, it still appears as though survival has improved simply because the diagnosis clock started earlier. This creates a false perception of benefit from the screening test. Selection bias. Specific types. Beyond general sampling issues, specific types exist. For example, volunteer bias. People who volunteer for studies may be different from those who don't. Bergson's bias. This is a specific type of selection bias that can occur when both the exposure and the disease under study increase the likelihood of admission to hospital. If you then conduct the study recruiting subjects exclusively from a hospital setting, you might find a spurious association between the exposure and the disease that doesn't exist in the general population, simply because people with both are overrepresented in hospitals.
Wow, that's a lot of ways a study can go wrong systematically. So if I read a paper, say, claiming a new screening test for an early cancer dramatically improves survival time compared to historical data, I immediately need to ask myself, Is this a genuine improvement in outcome, or am I just looking at lead time bias because they're diagnosing it earlier but not actually changing the course of the disease?
Exactly. Or is it length time bias?
Mm-hmm.
Another screening bias where screening tends to preferentially pick up slower growing, less aggressive cases, making the prognosis look better. You have to put on that critical lens and actively look for these potential biases that could undermine the study's internal validity, external validity, and ultimately its clinical relevance to your practice. That critical appraisal is essential. Hashtag TAC 5.3 screening metrics, 4x4 table analysis.
Okay, moving from study design flaws to the practical application of diagnostic and screening tests in the clinic. Everything here really boils down to understanding that 2x2 contingency table, or 4x4 table is sometimes called. We compare the test result, positive or negative, against the true disease status, disease present or disease absent.
Right. That gives us the four crucial categories. A, true positive, test is positive, disease is present. B, false positive, test is positive, disease is absent. Type I error for the test.
Yeah.
B, false negative, test is negative, disease is present. Type 2 error for the test. D, true negative, test is negative, disease is absent.
And from these four counts, A, B, C, D, we can calculate all the key performance metrics of the test. The sources emphasize categorizing these metrics into two conceptual groups: probabilities related to the person having the disease and probabilities related to the test result being correct.
Exactly. Let's start with the characteristics inherent to the test itself, often considered probabilities of the person. Sensitivity and specificity. These should, in theory, not change based on the prevalence of the disease in the population being tested.
Okay, sensitivity, what question does that answer?
Sensitivity answers. If a person has the disease, what is the probability that the test will correctly identify them as positive? It's the true positive rate. The formula is sensitivity equals A plus C. That's the number of true positives divided by the total number of people who actually have the disease. True positives plus false negatives.
And why is high sensitivity useful?
A highly sensitive test is good at picking up cases. If a test has very high sensitivity, a negative result is very reassuring. It means it's unlikely the test missed the disease if it was there. This leads to the mnemonic SNOU day for a highly sensitive test. A negative result rules OUT the disease. Useful for screening or when you really don't want to miss a diagnosis.
Okay, SNOUT for sensitivity. Now, specificity, what does that tell us?
Specificity answers the opposite question. If a person does not have the disease, what is the probability that the test will correctly identify them as negative? It's the true negative rate. The formula is specificity D plus B heated A, the number of true negatives divided by the total number of people who are actually disease-free. True negatives plus false positives.
And the clinical utility of high specificity.
A highly specific test is good at correctly identifying those who are well. If a test has very high specificity, a positive result is very convincing. It means it's unlikely the test is positive if the disease is truly absent, low false positive rate. This leads to the mnemonic SPN for a highly specific test. A positive result rules in this disease, useful for confirming a suspected diagnosis.
SPM for specificity. Okay, sensitivity and specificity are properties of the test. But in daily practice, when we get a test result back, we want to know something different, right? We want to know the probability related to that specific test result being true for this specific patient sitting in front of us. This brings us to predictive values.
Exactly. These are the probabilities of the test being correct, and unlike sensitivity and specificity, they depend heavily on the prevalence, or the pretest probability, of the disease in the population you are testing. The two key ones are positive predictive value, PPV, and negative predictive value, NPV.
Let's take positive predictive value, PPV, first. If my patient's test comes back positive, what does PPV tell me?
PPV answers the crucial question. Given that the test result is positive, what is the probability that the patient actually has the disease? The formula is PPV equals A plus B. That's the number of true positives divided by the total number of positive tests. True positives plus false positives.
So it's the proportion of positive tests that are truly positive, and this depends on prevalence.
Hugely. If you use even a very good test in a low prevalence population, like screening the general public for a rare disease, most of the positive results you get will actually be false positives. So the PPV will be low, even if sensitivity and specificity are high. Conversely, using the same test in a high-risk population, where prevalence is high, will yield a much higher PPV.
Right, no negative predictive value, NPV, if the test comes back negative.
NPV answers. Given that the test result is negative, what is the probability that the patient truly does not have the disease? The formula is NPV equals to DD plus C, the number of true negatives divided by the total number of negative tests. true negatives plus false negatives.
So it's the proportion of negative tests that are truly negative. And this also depends on prevalence.
Yes, but in the opposite way to PPV. In a low prevalence setting, a negative test result is more likely to be a true negative, so NPV tends to be high. In very high prevalence settings, NPV might decrease. But generally, NPV is the probability you can trust a negative result. Hashtag 5.4, likelihood ratios, LRs,
Yeah.
clinical utility.
Okay, sensitivity, specificity, PPV, NPV, they're all useful, but sometimes it feels like you need a calculator and the prevalence estimate to really use them effectively at the bedside. The sources mention likelihood ratios, LRs, as perhaps a more direct way to see how much a test result shifts our clinical suspicion. How do they work?
Likelihood ratios are really elegant because they combine sensitivity and specificity into a single measure that tells you how much a particular test result, positive or negative, modifies the probability of the disease being present. They directly quantify the diagnostic power of the test result itself, independent of prevalence.
Okay, so there's a likelihood ratio for a positive test, LR plus, and one for a negative test, LR.
Exactly. The likelihood ratio positive, LR plus, tells us how much more likely a patient is to have the condition given that they have a positive test result. The formula is 1 LR plus equals sensitivity, 1 specificity ratio. Remember, 1 specificity is the false positive rate. So it's the ratio of the true positive rate to the false positive rate.
Sensitivity divided by the false positive rate. And how do we interpret the LR plus value if the LR plus is, say, 5?
An LR plus of 5 means that a positive test result makes the odds of the patient having the disease 5 times higher than they were before the test was done, the pre-test odds.
Okay. And the likelihood ratio negative, LR.
The LR tells us how much less likely the patient is to have the condition given that they have a negative test result. The formula is 1 LR, 1 sensitivity, specificity LR, remember. 1 sensitivity is the false negative rate. So it's the ratio of the false negative rate to the true negative rate.
False negative rate divided by specificity. And how do we interpret LR values? They'll be less than 1, right?
Yes, useful LR values are less than 1. An LR of, say, 0.2 means a negative test result reduces the odds of the disease to only 0.2 times or 1/5 of what they were before the test.
So the general interpretation across both LRs. An LR of 1 increases the post-test likelihood of disease compared to the pre-test likelihood. An LR11 decreases the post-test likelihood. And what if the LR is exactly 1?
An LR of 1 means the test result provides absolutely no diagnostic information. The post-test odds are exactly the same as the pre-test odds. The test is useless in that case.
Now, for clinical practice and maybe for exams like the AKT, are there certain threshold values for LRs that indicate a test is particularly useful?
Yes, there are widely accepted rules of thumb. For the LR positive, LR plus, an LR plus $ greater than 10 is considered to indicate a large and often conclusive increase in the likelihood of disease. A test with an LR plus 10 can often rule in the diagnosis. LR plus values between 5 and 10 indicate a moderate increase. LR plus values between 2 and 5 indicate a small increase. LR plus values between 1 and 2 provide very little useful information.
Okay, so LR plus above 10 is powerful for ruling in. What about the LR negative LR?
For the LR negative,
LR.
an LR $ less than 0.1 is considered to indicate a large and often conclusive decrease in the likelihood of disease. A test with an LR Jazz 0.1 can often rule out the diagnosis effectively. LR values between 0.1 and 0.2 indicate a moderate decrease. LR values between 0.2 and 0.5 indicate a small decrease. LR values between 0.5 and 1 provide very little useful information for ruling out.
So LR plus a 10 and LR.1 are the key thresholds indicating a diagnostically very useful test result.
Exactly. Those are the numbers to remember. LRs are great because you can intuitively grasp how much a test result changes things, and you can even use them with nomograms or calculations to convert pre-test probability to post-test probability if needed. They directly measure the clinical utility of the test information.
Okay, our final section now zooms out a bit to look at population-level metrics like incidence and prevalence, touches on some healthcare economic measures, and then zooms right back into the crucial calculations that define the absolute impact of our treatments on patients, things like NNT, hashtag 6.1, incidence versus prevalence.
Right. Another cornerstone distinction we need to be absolutely clear on, especially from a public health perspective, is the difference between incidence and prevalence. They both measure frequency of disease, but in different ways.
Okay, let's start with incidence. What is it measuring?
Incidence measures the rate at which new cases of a disease or condition occur in a specified population over a defined period of time. It reflects the risk or probability of developing the disease during that time period. For example, we might say the incidence of type 2 diabetes in a certain region is 50 new cases per 1,000 people per year. It's about new occurrences.
So incidence is a rate focused on new cases. How does prevalence differ?
Prevalence measures the total number or proportion of individuals in a population who have a particular disease or condition, both new cases and existing cases, at a specific point in time, that's point prevalence, or during a specified period, that's period prevalence. It essentially measures the overall burden of the disease in the population right now. How many people are currently living with the condition?
So prevalence is more like a snapshot of who has the disease currently, while incidence is like a video camera recording the new cases appearing over time.
That's a good way to think about it. Incidence reflects the flow of new cases. Prevalence reflects the stock of existing cases.
And the sources mention a mathematical link between them, related to how long the disease lasts.
Yes, there's a key relationship, particularly for diseases in a steady state, where incidence and duration aren't changing rapidly. The formula is approximately prevalence, incidence times average duration of the disease.
Prevalence equals incidence times duration. How does that play out?
Well, think about a disease like the common cold or seasonal flu. It might have a very high incidence rate during winter, lots of new cases appearing quickly, but the duration of illness for each person is very short, maybe a week. So the prevalence at any single point in time might not be astronomically high, and it fluctuates rapidly.
Okay. What about a chronic disease?
Contrast that with a chronic disease like, say, type 1 diabetes. The incidence rate, number of new cases diagnosed each year, might actually be relatively low, but because the disease duration is lifelong, those cases accumulate over time. So even with low incidences, the very long duration leads to a high and stable prevalence, a large number of people living with the condition at any given time. Understanding this relationship is key to interpreting disease frequency data. Hashtag 6.2 healthcare economic measures.
Right. Now, moving into the reality of modern healthcare, decisions about treatments and interventions often involve considering not just clinical effectiveness, but also cost effectiveness and overall value. The sources mention two key metrics used in health economics, QLA and daily.
Yes, these are attempts to quantify health outcomes in a way that allows for comparison across different diseases and interventions, often incorporating quality of life. Let's start with QALY, the Quality Adjusted Life Year.
Quality adjusted life year. What does it adjust?
It's a measure that aims to combine both the quantity of life gained from an intervention, how many extra years of survival, with the quality of that life during those years. Quality of life is typically measured on a scale where 1 represents perfect health and 0 represents death. So 1 QALY is equivalent to 1 year lived in perfect health. A year lived with a disability or illness that reduces quality of life to, say, 0.5 would only count as 0.5 QALYs.
And how are QALYs used?
Healthcare systems and bodies like NICE in the UK often assess the cost-effectiveness of new treatments by calculating the cost per QALY gained. There's usually an implicit or explicit threshold. If a new treatment costs more than, say, £30,000 per QALY it provides, it might be considered not cost-effective enough for widespread adoption.
Okay, so QALYs measure health gain, incorporating quality. What about daily disability adjusted life year? That sounds like the opposite.
It is, in a way. Dailies measure the burden of disease. A daily represents the loss of the equivalent of 1 year of full health. It's calculated by summing two components: the years of life lost, LL, due to premature mortality, and the years lived with disability, YLD, for people living with a health condition or its consequences.
So YLL plus YLD equals daily.
Correct. One daily represents the loss of 1 year of healthy life. The goal of public health interventions, from a global perspective like the WHO often uses, is often framed as minimizing the total dailies caused by various diseases and injuries in a population. It helps prioritize health problems based on their overall impact on both mortality and morbidity.
Got it. QALYs measure gain, dailies measure loss or burden. The sources also mention the standardized mortality rate, SMR. What's that comparing?
The SMR is used to compare the mortality experience of a specific group or cohort, for example, workers in a particular factory or residents of a specific town, to that of a standard reference population, often the general population of the country. It's calculated as the ratio of the observed number of deaths in the study cohort over a period to the expected number of deaths in that cohort if they had experienced the same age and sex-specific death rates as the standard population during that same period.
So 7-MAR exerts expected deaths, and it's often expressed as a percentage or multiplied by 100.
Yes. So an SMR of 100 means the mortality rate in the study cohort is exactly the same as expected based on the standard population. An SMR less than 100 indicates that the cohort experienced fewer deaths than expected. A healthy worker effect is a common reason for SMR 100 in occupational cohorts. And an SMR greater than 100 means the cohort suffered more deaths than expected, suggesting an increased risk associated with being in that cohort. For example, exposure to a hazard. It's a way to adjust for age and sex differences when comparing death rates between populations. Hashtag 6.3 calculating risk and odds.
Okay, let's quickly revisit the calculation of risk and odds, making sure we're clear on the link to study design.
Absolutely. Just to reiterate that key linkage. Risk, which is essentially a probability, is typically calculated in prospective studies like cohort studies, where you follow a group forward to see who develops the outcome among those initially at risk. Odds, on the other hand, are calculated in retrospective studies like case control studies, where you start with cases and controls and look back at exposures.
And the calculation itself, how do we calculate risk?
Risk, or probability, of an event is calculated simply as the number of people who experience the event divided by the total number of people initially at risk of experiencing that event. Risk, events total, at risk.
Okay, events total at risk. And how do we calculate odds?
Odds are calculated slightly differently. The odds of an event are the number of people who experience the event divided by the number of people who do not experience the event, the non-events. Odds, events, non-events.
Events, non-events. Let's use that example from the source material to see the difference. Say, out of 200 patients receiving a new gout drug, one patient develops a serious adverse event like a PE, pulmonary embolism, during the study period. What's the risk and what are the odds?
Okay, the risk of developing a PE in this group is the number of events. 1 divided by the total number at risk, 200. So risk at 0.00, some 0.0055, or 0.5%.
And the odds. That would be the number of events, 1 divided by the number of non-events. How many non-events were there?
If one person had the event out of 200, then $200 one equals 199 people did not have the event. So the odds of developing a PE are $1.599.
1 divided by 199 is approximately 28.005025. So very close to the risk in this case.
Exactly. When the event is rare, like in this example, only 1 or 200, the number of non-events, 199, is very close to the total number at risk, 200. As a result, the odds and the risk will be numerically very similar. This is why odds ratios, calculated from case control studies, are often used as an estimate or proxy for risk ratios from cohort studies when the disease or event is rare in the population. However, it's crucial to remember the conceptual difference and that they come from different study designs. And if the event is common, the risk and odds values can diverge significantly. Hashtag 6.4, comparing groups, ratios, and impact.
Right. Now, the really important part for clinical practice, comparing the event rates between two groups, like a treatment group and a control group, to see the impact of the intervention. We need to define the event rates in each group first.
Yes, we typically need two absolute measures. The event rate in the control or comparison group, often called the control event rate, CER, and the event rate in the exposed or experimental group, called the exposed event rate, EER, or sometimes experimental event rate. These are just the risks or proportions calculated as events total in each respective group. Okay, CER and ER, once we have those, we can calculate ratios like the risk ratio or odds ratio to compare them. How do we interpret these ratios? Whether it's an odds ratio, usually from case control or cross-sectional studies or logistic regression, or a risk ratio, usually from cohort studies or RCTs, the interpretation of the ratio value itself follows the same logic, using 1 as the point of no difference. An ERE at one end indicates that the event is more likely or more frequent in the exposed experimental group compared to the control group. And ER indicates there is no difference in risk or odds between the two groups. This is the null value. And ER1 indicates that the event is less likely or less frequent in the exposed experimental group compared to the control group, suggesting a protective effect.
So a ratio tells us the relative difference. But for clinical decisions, we often need to know the absolute impact, right? This brings us to metrics like absolute risk reduction and NNT.
Exactly. These are arguably the most important metrics for translating research findings into meaningful clinical practice decisions. Let's start with absolute risk reduction, ARR.
How is ARR calculated?
ARR is simply the raw absolute difference in the event rates between the control group and the experimental group, assuming the event is undesirable, like death or relapse. AR equals CR. AR. For example, if the risk of stroke in the placebo group, CER, is 10%, and the risk in the new drug group, ER, is 4%, then the AR is 10%, 4% is 6%. The drug reduces the absolute risk by 6 percentage points.
Okay, ARR is simple subtraction, and this absolute number feeds directly into what many consider the single most critical metric for clinical practice, the number needed to treat, NNT.
Yes. The NNT tells you how many patients you would need to treat with the experimental therapy compared to the control therapy for a certain duration to prevent one additional undesirable outcome. It's calculated very simply as the reciprocal of the ARR. NNT equals 1 ARR. Remember to use the ARR as a proportion. For example, 6% equals 0.06 in the calculation.
So using our example where ARR was 6% or 0.06, the NNT would be 0.06x's.
Which is approximately 16.7. We usually round NNTs up to the nearest whole number, so the NNT would be 17.
And the interpretation, an NNT of 17 means?
It means you would need to treat 17 patients with the new drug instead of placebo for the duration study to prevent one additional stroke. A low NNT, previously 2 or 3, indicates a very effective treatment with a large absolute benefit, providing a strong clinical incentive to use it. A high NNT, equals 50 or 100, suggests the absolute benefit for any individual patient is quite small.
NNT is incredibly useful. Now, what about the flip side? What if we're looking at harm or adverse events?
We can calculate similar metrics. The attributable risk, AR, sometimes called absolute risk increase, ARI, measures the excess risk associated with the exposure or treatment, usually calculated as $1. It was EAR/SEER when the event rate is higher in the exposed group.
So AR is the absolute increase in risk due to the exposure treatment, and its inverse gives us the number needed to harm NNH.
Exactly. None NH equals 1 AR. This tells you, on average, how many people you would need to treat or expose before one additional person experiences a specific harmful event compared to the control group. For NNH, you obviously want the number to be very high, suggesting the treatment is safe and harms are rare.
Okay, ARR and NNT for benefit, AR and NNH for harm. These focus on absolute differences. What about relative differences again? We sometimes see relative risk reduction, RR, reported. How is that calculated?
RR tells you the proportion by which the risk is reduced in the experimental group relative to the control group. It can be calculated in two main ways. Free, CR-ERS, or RE-ERS, or a noun chair, or R is the risk ratio, ERSR.
Let's use our stroke example again. CER equals 10%, 0.10, ERO equals 4%, 0.04. The ARR was 6%, 0.06. What's the RRR?
Using the first formula. Coin R, 0.10, 0.10, 0.10, 0.10 equals 0.66, or 60%.
And this highlights a really important point, doesn't it? The RRR of 60% sounds incredibly impressive, much more dramatic than the ARR of 6%.
Exactly. This is why RRR can sometimes be misleading if presented on its own, especially if the baseline risk, CER, is very low. A drug could achieve a large RR, like 50%, but if the absolute risks involved are tiny, for example, reducing risk from 0.0003% to 0.0001%, the ARR is minuscule, 0.0001%, and the NNT would be enormous, 1 million, meaning the clinical impact is negligible despite the impressive-sounding relative reduction.
So as clinicians, we should always look for the absolute risk reduction, ARR, and the number needed to treat NNT to understand the true magnitude and clinical significance of a treatment effect rather than relying solely on the relative risk reduction.
Absolutely. ARR and NNT give you the bottom line impact for your patients. We can also calculate relative risk increase, RRI, if the risk is higher in the experimental group, usually as 3R is EAR/SEER, or RI equals RR11.
Okay. One last ratio mentioned is the hazard ratio, HR. How is that different from a risk ratio?
Hazard ratios typically come from survival analysis, using methods like Cox proportional hazards regression. A hazard is the instantaneous potential or probability of an event, like death or disease recurrence, occurring at a particular point in time, given that the individual has survived up to that point. The hazard ratio, HR, compares the hazard rates between two groups, so treatment versus control, over the course of the study.
So it's like a ratio of risks, but it accounts for the timing of events.
Essentially, yes. And when HR equals 11:1, it means the hazard rates and thus survival experience are the same in both groups over time. And YRR equals 0.555 would mean that at any given time point during the study, individuals in the treatment group have half the hazard, half the instantaneous risk of experiencing the event compared to individuals in the control group. And YHR equals 22 would mean double the hazard. It's interpreted similarly to RR, but it's derived from time to event data. #tagoutro.
Well, we have certainly completed a comprehensive journey today, haven't we? We've really dug into the statistical backbone of clinical practice. We defined the geometry of data, navigated pretty much the entire test selection matrix from the Mann-Whitney U test right through to the McNamara test. And we explored the research methodology that defines the quality of evidence, including the limitations of those 3Cs observational studies and the absolutely critical importance of intention to treat analysis in trials.
We did. And we also pinned down those essential clinical metrics that you need every day. The crucial difference between sensitivity and specificity, the immediate practical utility of likelihood ratios, especially remembering those key thresholds of LR plus 10EQ, $10, and LR let eat or let 101 books, and, of course, translating research into real impact via the absolute risk reduction and the number needed to treat. Hopefully this knowledge serves as your license to critically engage with, rather than just passively absorb medical information you come across.
Yeah, this isn't just theory for the exam, is it? We really encourage you, maybe the next 3 articles you read, to actively try and identify the data types being used. Ask yourself, what statistical test did they apply? Was that test actually appropriate given the data they had? Did you check if the confidence interval crossed the null value? Could this study be suffering from, say, lead time bias if it's about screening, or maybe recall bias if it's a case control study? Start applying that critical lens.
Absolutely. And as we conclude this deep dive, we want to leave you with one final provocative thought, something that really brings the whole session together, connecting the statistics to your practice. When you read a paper, you're inevitably confronted with both measures of statistical significance, typically the p-value, and measures of clinical significance or effect size, like the NNT or the ARR. So the question to ponder is this: which single calculation, the p-value or the NNT, actually tells you more about whether you should seriously consider changing your clinical practice tomorrow based on that paper, and why?
That's a really good question. Thank you for joining us on the deep dive. That's definitely something worth mulling over during your next clinic shift or journal club.